In this section, we're going to review inverse functions. So you probably covered this in one of your algebra classes if you took pre-calculus, but if you didn't, we'll cover it as if you'd never seen it before. So to start off, let's look at the definition of inverse functions. A function g is the inverse function of the function f when f evaluated at g of x is equal to x for each x in the domain of g, and when g of f of x is equal to x for each x in the domain of f, and the function g is denoted by f with this -1 power here, but that's read f inverse. So one thing that's important to note here, just notationally, f inverse of x is not 1 over f of x. That does not mean the same thing. So don't read too much into the -1, it's just a notation. So basically what's going on here is you can think of a function and its inverse as kind of undo buttons for each other. So if you plug a value into one of the functions and then you plug the output of that into the other function, you should get what you started with. So in order for this to be the definition to hold, specifically both of these compositions have to actually be x. It's not enough for them to just be the same. It's not enough for them to be some other value. It has to specifically be x. Now, some interesting things about f and f inverse that we'll kind of come across is that if you know the domain and the range of f, so let's say the domain of f is some set A and the range of f is some set B, then you also know the domain and range of f inverse. They just swap places. So if you had, for example, a set A where you had the numbers 1, 2, 3, 4 in your set A, and I'm just going to draw a bubble around it, and your set B was the letters A, B, C, D. If you're defining a function f from A to B, let's say 1 maps to B, and 2 maps to A, and 3 maps to C, and 4 maps to D, then f would contain the ordered pairs 1b, 2a, 3c, and 4d, whereas f inverse would go in reverse, and it's just like you turn all of those arrows around. So that would contain the ordered pairs b1, a2, c3, and d4. So you can see if you have xy is an ordered pair of f, then yx is going to be an ordered pair of f inverse. Using the definition, I'm going to verify that two functions are inverses of each other. So I'm going to take f and plug g of x into it. So that will be f evaluated at 3 minus x over 4. So everywhere that I have an x, I'm going to replace it with 3 minus x over 4. So you'll see that the 4's cancel, and I have 3 minus 3 minus x. If I distribute, that's 3 minus 3 minus negative x, so plus x, which is x. So we get what we want there. If I'm going in the opposite direction, I'm going to take g evaluated at f of x, and wherever there's an x in this function, I'm going to replace it with 3 minus 4x. So this will be 3 minus 4x over 4. So again, I'm going to distribute, so I have 3 minus 3 plus 4x divided by 4, or 4x over 4, or x. So since we have f of g of x equals x and g of f of x equals x, we can say that f and g are inverses of each other. The reflective property of inverse functions says that the graph of f contains the point AB if and only if the graph of f inverse contains the point BA. So if you have the function f, which is the ordered pairs 2 to 3, 1, 4, negative 1, 6, 0, 2, and 3, 5, if I want to find the domain and range of f, so for f, the domain is a set of all x values, and I am going to try and put them in order. So that'll be negative 1, 0, 1, 2, 3. And the range would be the set of all y values. So I would have 2, 3, 4, 5, and 6. I can either just flip those to find f inverse, or I can look at the ordered pairs of f inverse. The inverse function, it does tell me to find that, so that would be 3, 2, just flipping the ordered pairs, 4, 1, 6, negative 1, 2, 0, 5, 3, and the domain is going to be 2, 3, 4, 5, 6, and the range is going to be negative 1, 0, 1, 2, 3. So you can see that they do swap places. Now, because the ordered pairs swap places, basically what's going on, if you know the graph of f of x, you can find the graph of f inverse of x by swapping all those ordered pairs, swapping the x and y. So basically the graph is reflecting over the line y equals x. And it's also worth noting that the graphs of inverse functions do have reciprocal slopes. So you would expect that that would happen. And we'll get to that more later on when we talk about the derivatives. Now, a very important part of this is that not every function has an inverse. So how do we know if a function has an inverse or not? Well, this theorem says that a function has an inverse function if and only if it is 1 to 1, and if f is strictly monotonic on its entire domain, that it's 1 to 1 and therefore has an inverse. So, kind of some terms here. Monotonic means f is either non-increasing or non-decreasing on its entire domain. And when I say non-increasing or non-decreasing, choose one for the entire domain. It's not switching back and forth. And strictly monotonic means f is either increasing or decreasing on its entire domain. So when we talk about monotonics, that's what we mean. So the other term that we use here is the idea of a one-to-one function. And a function is 1 to 1 if for every y value there's exactly one x value in the domain such that f of x is equal to y. So for example, a function like this where I have 1, 2, 3 as my domain and my range has 2, 4, 6, and let's say we map 1 to 4, we map 2 to 2, and we map 3 to 6. This would be a one-to-one function because for every x value there's clearly exactly one y, but it also works in reverse. For every y value there's only one x. Whereas with this function, let's say I have 1, 2, 3 again, and my range in this case is going to just be 4 and 5, where I have maybe 1 mapping to 4, 2 mapping to 5, and 3 mapping to 5. This is a function, but it's not a one-to-one function because 5 going in the reverse direction, 5 would be paired with both 2 and 3 in the x. So this is not one-to-one, but it is a function still. Now, anytime you have a graph of a one-to-one function, it will pass what's called the horizontal line test. So remember, the vertical line test lets you look at a graph and see whether or not the graph represents a function. If you pass a vertical line through the function, at any point it will only hit the function in no more than one place. Whereas a horizontal line test tests for one-to-oneness, and it's basically testing for whether or not the inverse is also a function, if there is one. So in this case, we would fail the horizontal line test for this graph because when we pass a horizontal line through, we hit the graph 2 times in at least one location. So this particular function here does not have an inverse. Now recall that to be strictly monotonic, we defined that earlier as saying that a function must be either increasing on its entire domain or decreasing on its entire domain. So you can see this function right here is strictly monotonic, and it would be one-to-one. It would pass the horizontal line test. This function is not one-to-one, and it's also not strictly monotonic. So you can see that it's going up and then decreasing and then increasing again. So this one does not have an inverse function. It would fail the horizontal line test. Now if you want to find an inverse function, if you know that a function is not one-to-one, you don't even have to bother. You can say that there's no inverse function. But if you can determine that there is an inverse function, you can start by solving for x as a function of y. So you would replace your f of x with a y, and then you would solve for x. And then you can swap x and y and replace the y with f inverse of x. And then you would want to find the domain, and you probably want to verify at least that your work is correct. So for example here, it says find f inverse if it exists, sketch the function in its inverse. This is a straight line. It's going to have a slope of +2, so it is going to be one-to-one. You're not going to have any issues with failing the horizontal line test. So for step 1, it's a straight line, which means that it's one-to-one, which means that it has an inverse. So step 2, I'm going to replace y, or replace the f of x with y, and then I'm going to add 3. So I get y plus 3 equals 2x, and then I would divide by 2. So I would get y plus 3 over 2 is equal to x. And then step 3, I'm going to replace the x and the y, I'm going to swap them. So I would get that x plus 3 over 2 equals y, or y equals x plus 3 over 2. And I would recall that as f inverse of x. Okay, so that's my inverse. So for step 4, well, we want to look at the domain and the range. So f is a polynomial, it's a straight line, so its domain and its range are -infinity to infinity. So that means that if you were to swap those two, the domain here and the range are both -infinity to infinity as well. So for step 5, if we want to verify, that's pretty straightforward. We would say f of x plus 3 over 2, which would be 2 times x plus 3 over 2 minus 3, which is x plus 3 minus 3, which is x. And g of 2x minus 3 would be 2x minus 3 plus 3 over 2, which is 2x over 2, which is x. So that one works out as well. And it does ask to sketch the function in its inverse. So if I were sketching 2x minus 3, um, 2x minus 3, I would go down to -3, and then I would go up 2 over 1, up 2 over 1. So that would be this line right here. And I could just swap all of the ordered pairs. So instead of 0, -3 here, I would have -3, 0. And instead of, let's see, 1, -1, I would have -1, 1. And instead of 2, 1, I would have 1, 2. So this would be my inverse here in red. And you can see if you sketch out, which it would be a little bit better if my graph were completely perfectly to scale, but you can see that you can sketch out the line y equals x, and it does reflect across that line. So for this one, if I were verifying that this thing was one-to-one, sometimes it might actually help to graph it. So this is the square root of x squared minus 4, and if I were to graph this, I would get a graph that looks roughly like this. So this is definitely a one-to-one graph, especially on the domain where x is greater than or equal to -2. So this is one-to-one, and it does have an inverse. So for step 2, I would say y equals the square root of x squared minus 4. I would square both sides. I would add 4. I would take the square root. Now normally when you take a square root, you have to consider the plus or minus. But in this case, because we know that the domain and the range of f and f inverse are going to swap places, the domain here was from 2 to infinity, and the range you can see from the graph is from 0 to infinity. We know that our domain for f inverse is going to be 0 to infinity, and our range is going to be 2 to infinity. So when we swap this, we're going to have y equals the square root of x squared plus 4, and we don't need this since we know that y is greater than or equal to 2. So f inverse of x is going to be the square root of x squared plus 4, and we do have this restriction here that x has to be greater than or equal to 0. So even though the graph of x squared plus 4, or the square root of x squared plus 4 could exist for negative x's, we don't include those because it wasn't part of our allowed domain. So what ends up happening is that the graph of this function only starts at 0, and it ends up looking like this. So that would be my inverse for this problem. Now let's say I wanted to find the inverse of f of x equals x squared. Well, we know what that looks like if you graph it. It's a very simple graph. And it looks roughly, close enough, like this. So this one is not one-to-one, so it has no inverse. However, if we were asked to find the inverse of f of x equals x squared with the imposed limited domain that x is greater than or equal to 0, we would only be looking at this half of the function. So you can see that as defined here, this function is one-to-one. So we can actually do this. It's worth talking about the domain and the range, because the domain here is going to be from 0 to infinity. The range is also from 0 to infinity. So those are going to swap places. So our domain is also going to have to be 0 to infinity for our inverse. So I would start off with y equals x squared. The square root of y would be equal to x, and again we don't need the plus or minus because y is greater than 0 here. So y is going to be the square root of x, and f inverse of x is the square root of x, and of course we have to include the fact that x has to be greater than or equal to 0. So if you were going to graph this, it would look roughly like this.